Hello students, welcome to the class. So today we will be doing section 6.11 of the chapter 6 equilibrium in our theory part 9. So this is the disclaimer. Now in this class our objective would be to differentiate between monobasic and polybasic. So depending upon the uh, type of structure on which we are looking on, we can divide our structure, or you can say divide our acid on the basicity as monobasic and polybasic. Apart from this, we will look on to a very important topic, which is common ion effect. So we will see that how the common ion effect has an impact on the degree of ionization of a weak acid or a weak base. So let us look at the specific sections of the NCERT that we are going to cover. So we are going to cover the section number 6.11.6, which is di and polybasic acids and di and polybasic acidic bases. Then we have the factors affecting acidic strength. And lastly, we have the 6.11.8 common ion effect in the ionization of acids and base. Apart from this, we will do also an NCERT problem 6.17. So let's start with the polybasic acids. So there is a very simple definition of it, although the concept is somewhat difficult to get. But the definition says that if your acid can donate more than one proton, then we call that acid as polybasic acid. We know that from the Arrhenius definition that acids are those substances that can donate H+. Now, if your molecule is donating more than one H+, then you tell that molecule is polybasic in nature. Here, the removal of this H+ takes place in various steps. Now, the question is that are all the protons that are available or all the hydrogens that are available in the given structure are ionizable? No. Only those which have a very specific connection, which is what? Which is connection to a specific atom are considered as ionizable, and that connection is to oxygen. Now, this is a general perspective. There may be a place where that hydrogen is ionizable, where it is not attached to oxygen. So I'm talking about the polybasic. But in most of the polybasic acids, only those hydrogens are ionizable which are directly attached to oxygen. For example, if you take sulfuric acid, then it has two ionizable protons. But in this case, we are seeing that all the protons, which is 2, is ionizable. But this thing is not true for all the cases. Now, why I am saying it that 2 protons are ionizable? Because it is a dibasic. So this word dibasic is indicating that 2 protons can be removed from this sulfuric acid, right? Here are some more examples of this polybasic acids. We have oxalic acid, carbonic acid, sulfuric acid, phosphoric acid, and phosphorus acid. What we can conclude from this slide? So a very important discussion, which is saying that all the acids which can donate more than one proton are polybasic, and all the protons present in a structure are not necessarily ionizable. So the number of ionizable proton can be equals to the number of hydrogen present in the molecule, or it can be less also. Got it? Now we will try to understand this with the help of a specific example where your number of ionizable proton is less than the number of hydrogen in the structure. For that, we will take the example of phosphorus acid, whose formula is H3PO3. Now, what is your expectation? You would expect that it has 3 hydrogens, so it should be triprotic. Therefore, it must have 3 ionizable protons. But in reality, it is diprotic. It can only ionize two hydrogens. And what is the reason behind it? Just look at the structure. What you can see in the structure? You can see that only two hydrogens are there which are attached to the oxygen directly. The third hydrogen is not attached to oxygen, instead, it is attached to phosphorus. And that is the reason H3PO3 has only two ionizable hydrogens. Got it? So it is very important to decide the basicity of a given acid, and that can be only done by drawing the proper structure. Got it? Similarly, we have polyacidic bases. Here, the bases can donate more than one hydroxide ion. And this ionization again takes place in various steps. For example, we have this calcium hydroxide, zinc hydroxide, and aluminium hydroxide. So calcium hydroxide is diacidic, zinc hydroxide is diacidic, and aluminium hydroxide is triacidic. In the case of bases, there is no presence of a proper trick to do it. That, okay, like in the case of acid, you said that, okay, if your hydrogen is attached to oxygen, then in that case it is ionizable. But here, we don't have any such generalization. But although you can get an idea by looking at more examples. For example, in this case, both of the hydroxides are directly, or you can say they are donating their proton onto their electron onto the calcium, and they are present as one unit. Right? This is the reason they are ionizable. I hope you got this idea of polybasicity and polyacidity. Moving on to the ionization part. We said that in the definition that your ionization of a polybasic acid takes place in various steps. So let us try to quantify those steps. For that, we have taken the example of carbonic acid, which is a dibasic acid and whose formula is H2CO3. Now, in this case, we will try to represent the successive ionization of carbonic acid. So first of all, we will remove one of the hydrogen from this H2CO3. What it will result in? Upon the removal, this H plus will go on to H2O, making it H3O plus, whereas the carbonic acid will be converted to HCO3 minus. The negative sign is of course coming due to the electron that is being released by the H plus upon removal, and that is creating one extra negative charge. And you can clearly see that one of the hydrogen is removed. Now this process is in an equilibrium state. Why? Because this process is not going on to its completion because of its weak acidic property. Can we represent the above situation with the help of equilibrium constant? Yes, we can write it as the first ionization constant, which is a kind of equilibrium constant again, Ka1 for the first step. Here we have neglected H2O concentration because it is almost constant. We have taken the concentration of H3O plus and HCO3 minus, which is product, on the numerator, and in the denominator we have taken H2CO3 concentration, which is carbonic acid. But we are left with one more hydrogen that can be ionized in the case of HCO3 minus. So in the next step, we will do that. We will again react our HCO3 minus with H2O, and that will result in the removal of the second proton as well. As a result, we will get H3O plus again in the product along with the carbonate ion, which is CO3 2 minus. We can again represent this whole situation of step 2 with the help of ionization constant. We will name it as second ionization constant, Ka2, and that will be equals to H3O plus multiplied by the CO3 2 minus concentration divided by the HCO3 minus concentration. See how we have removed two protons in a successive manner. And in addition to that, we have also two different ionization constant. Now the next part is to compare this ionization constant, that whether the K1 will be the smaller one or the K2 will be the smaller one, or there is no definite pattern for it. For that, we will again take one more example, a general one, where our polybasic acid is having n number of ionizable protons and it is attached to an anion which is A. Then we can represent the first proton removal as HNA going to H plus and HN minus 1, and A is having a power of negative, means 1 negative charge, right? Now next thing you should notice here is that we have not taken H2O. Okay, it is not important in this case. In previous case also you can take the acid alone, but to represent it in a more standard manner, we represent it with the help of H2O. Here I have directly taken the ionization part. Upon removal of one proton, now the total number of proton left in your given molecule will be n minus 1. Here we have represented the ionization constant as Ka1. Similarly, if I write it for the second proton removal, we can write it as Hn minus 1 having a negative charge is releasing one proton to give Hn minus 2, means here two protons are removed. Whereas the charge which is accumulated on the given species will be minus 2 due to removal of two protons. Let us suppose that the ionization constant is K2. Moving on further, we can remove the last proton and we can finally get a power of n minus on the A, right? And in this case, we are representing the ionization constant as An. Okay, we are representing the ionization constant as Kan. Is it clear? So, what is the comparison of these three equilibrium constant K1, K2, Kn, or you can say we can have K1, K2, K3 up to Kn. Got it? So, I have not written the intermediate one. It is self-explanatory, I suppose. So, the general trend says that the successive ionization constant always decreases. Means K1 will be greater, then we will have a smaller K2, then we will have a smaller K3, and lastly, we will have a smaller Kn. Okay? So, this is the general trend which is seen for acids as well as bases. Now, why it is happening? Let's see. If you look in the second step, then you can clearly see that we are removing a proton, a positive charge, from already negative charged species. The idea is that if you want to make a species stable, you want to make it uncharged. That means you should remove its charge or remove the negative charge in the case of second step. But instead of removing that negative charge, you are assigning one more negative charge onto that. So this process will result in an unstable molecule as compared to the first one. And that is the reason we are seeing that the product formation is less as compared to the first one. And so we have a K1 value greater than K2. This is totally happening due to the electrostatic attraction between anion and proton, which is already having a negative charge and we are removing a proton from it. Therefore, the same logic can be applied onto the third ionization constant and up to the nth ionization constant. So this is very, very important conclusion for polybasic acids and bases. And a second important point I would say is that most of the H plus that you would see in the solution will be coming from the first ionization, because the second and the next successive ionization are almost neglectable, right? As a result of it, most of the H plus concentration is coming from the first dissociation step. I hope this point is clear to you. Got it? Now moving on further, we have this result. Can we see some examples of it? So here is a table for you. We have oxalic acid, ascorbic acid, sulfurous acid, sulfuric acid, carbonic acid, and citric acid and phosphoric acid. you can see very clearly that the Ka1, suppose we are considering for phosphoric acid, it is 7.5 into 10 to the power minus 3. If you move on to the K2 of the same species, then it is very, very small, which is 6.2 into 10 to the power minus 8. And further, it decreases to 4.2 into 10 to the power minus 13, which is even smaller. Now, these are some specific example. You can also look at one more example. Suppose oxalic acid, if you look, it is having a K1 as 5.9 into 10 to the power minus 2, whereas the K2 is 6.4 into 10 to the power minus 5. Again, this is getting a smaller value. Now you can compare it for ascorbic, sulfurous, sulfuric, carbonic, and citric and acid and phosphoric acid as well. You will get the same result, that your K1 will be, for a specific acid I am saying, K1 will be greater than K2 and K2 will be greater than K3 and so on. Until and unless you have the presence of ionizable proton, you can see that this trend is followed. Moving on to the factors which affect the acidic strength. So this is also very, very important. The first factor is the bond strength. Suppose if your element is belonging to the same group and the size of the anion is increasing, means the part that will become an ion, that size is increasing, then in that case it is seen that the acid becomes stronger and stronger. For example, if you take the case of halogen acids, then Hi is the most strongest acid. What is the reason behind it? The reason is the greater size of the anion results in a weaker bond due to large bond length. Okay, therefore your Hi will have the weakest bond, then your HBr, then your HCl and an HF. As a result, it is easier to break the bond and release the H plus, resulting in a greater acidity. So this is the first factor. The second is the bond polarity. It is applicable for the elements which are present in the same period. So if your atom is having a greater electronegativity, it will have a greater tendency to become an ion and hence to release H plus, resulting in a much more greater acid. For example, if you take the example of methane, then ammonia, then water and HF, then the fluorine has the highest electronegativity and hence it has the highest acidity. Then comes your water, then your ammonia, and then for methane. Remember, this is only applicable to the compounds in which the central element is of the same period, like in this case. So these are all the members of the second period, if you know. Third one, if you are considering your oxo acids. So what are oxo acids? So they are those species which have one oxygen atom, then another heteroatom. Here it is represented as Y, and that O is attached to a H, which is of course ionizable. We can take phosphorus acid as example. For example, it is H3PO3. So here the Y is P, then we have oxygen, and then we have the hydrogen. In this case, if you want to compare the electronegativity, you should remember that the central atom should be same. Suppose we are taking the example of central atom as what? Fluorine. Then the acidic strength increases with the increase in number of oxygen atoms, because the oxygen atoms pull electron density more towards it and making it more polar and weaker. Right? Now, student make mistake of considering that due to greater number of ionizable proton, the system or the acid is highly acidic. But the reason is what? The reason is the greater pull of the oxygen and not greater number of ionizable proton. Right? So you should remember this. For example, HClO4 is having the highest acidity, then the HClO3, HClO2 and the HClO. So why it is occurring? Because of the greater number of oxygen atom which pulls the electron due to its higher electronegativity, making the release of hydrogen easier. So why I am saying it? Because greater number of ionizable proton has no impact on what? Acidity. because most of the proton is coming from the first ionization and not the successive one. The only reason the oxygen addition is making this substance more acidic is your greater electronegativity and greater polarity of the OH bond. I hope this point is clear to you. Now moving on, I would say to the most important topic of today's class, which is common ion effect. What does it say? According to this, we are seeing a separation in the ionization of a weak electrolyte whenever we add a common ion onto it. Now, this result is a direct consequence of the Le-Chatterjee principle. So basically, what are you doing? Suppose your given compound is dissociating into cation and anion. Now you're adding more anion. That means you're adding more product. Therefore, the reaction will proceed in backward direction to suppress that change. Let us try to understand this thing with the help of a example. Here we are taking the acetic acid's dissociation. How it will dissociate? It will dissociate as H plus and acetate ion. Now, suppose we disturb this equilibrium by adding the acetate ion, which is a strong electrolyte. So here we are adding the salt of sodium. Now what will happen? There will be an increase in the common ion because your acetic acid is also donating the acetate ion, plus your acetate, sodium acetate is also donating the acetate ion. Therefore, we have a common ion between these two compounds, and that will result in a separation of the dissociation of acetic acid, because salt is always completely ionizable. We know it for sure. The only thing that can keep the equilibrium constant in check is your less dissociation of acetic acid. How can we see it? So we can see it through the lens of Le-Chatterjee principle, that if you are disturbing the equilibrium by adding more product, the reaction will move on to the backward direction to consume that extra amount of product you have added. Got it? As a result, what will happen? If the reaction will move backward, that means less acetic acid will be dissociated and the H plus concentration will decrease. Second, if H plus is decreasing, that means your pH will increase, because pH is nothing but the negative logarithm of H plus. Third thing is that, which is obvious, which is ionization of acetic acid is suppressed. Got it? So what are we doing now? We are trying to see the exact effect through the calculation. For that, we will again consider the example of acetic acid. Here, we will take two cases. In first case, we are only taking 0.05 molar acetic acid in a vessel. In the second case, we are taking the acetic acid 0.05 molar, and apart from it, we have added acetate ion, which is 0.05 molar. Now we have two conditions. Suppose we want to calculate the pH in both the conditions, and first we are considering it for the case 1. How do we calculate it? It's very simple. So this is the dissociation of your acetic acid, which is represented here as HAC. So it will give you H plus and AC minus. Now next, if you want to calculate the pH, you have a general formula in terms of Ka, which is pH is equals to minus log Ka into C. Then putting the value of Ka, which is K is your dissociation constant, and its value is 1.8 into 10 to the power minus 5. What about concentration? In the start, I have told you that the concentration will be 0.05. If you put both of these values in the above formula, you will get your pH as 3.02. So this is your first calculation for the pH of simple acetic acid without any common ion effect. Now in the next case, what we are doing? We are adding this common ion, which is present in the concentration of 0.05 molar in the solution. Then, if you represent this whole scenario in a table, then we can represent it here. Suppose we have initially 0.05 molar of acetic acid, and we have added the 0.05 molar of acetate ion. After some time, the reaction will proceed, or you can say the ionization will occur, and X amount of this acetic acid will be dissociated to give us X amount of H plus and 0.05 plus X amount of AC minus, because initially we already have this 0.05, so X will be added to it. Remember, students, this is coming from the equivalence, because one equivalence of HAC will give you one equivalence of H plus and one equivalence of AC minus. Therefore, X equivalence of HAC will give you X equivalence of H plus and X equivalence of AC minus. Further, can we write the ionization constant for the above situation? Yes, it's very simple. That will be the concentration of H plus multiplied with the concentration of ASC minus divided by the concentration of the acetic acid. So this will be the final formula, X into 0.05 plus X by 0.05 minus X. How are we writing it? We know it very well that K is nothing but an equilibrium constant in which we take the concentration of the product divided by the concentration of reactant. Okay. Further, what we do is we approximate this whole formula. How do we do it? We say that, okay, the dissociation will occur only to a small extent. We know it very well. Therefore, your X will be less than 0.05. Then what we can do? We can keep 0.05 plus X or 0.05 minus X simply as 0.05, because your X is very, very small as compared to the 0.05 value. If we substitute this situation back to our previous equation with K value as 1.8 into 10 to the power minus 5. Now here the question is that, why are we taking the same value of K? In the previous one we have taken this same value. Why are we taking that same value? Because equilibrium constant has no effect on such on such changes of concentration, right? Therefore, this will remain same. And finally, if you put this as 0.05 instead of 0.05 plus X and 0.05 minus X, then this both will get cancelled out and you will get your X value as 1.8 into 10 to the power minus 5. I hope I am clear on this point. We got the value of X. If you remember the table, then this X is nothing but your concentration of H plus. See? So we can write now that the concentration of H plus will be 1.8 into 10 to the power minus 5. If I know the H plus, we can use the formula of pH according to the definition as minus log H plus, and you will see that minus log of 1.8 into 10 to the power minus 5 will give you a pH value of 4.74. So we calculated the pH in both the cases. First, with a common ion for the case 2 and without a common ion in the case 1. Now, the time is for the comparison. When we will compare with this both, we will see that in case 1, without the common ion effect, the value was 3.02, whereas with the common effect, this value increased to 4.74. So the pH is increasing. If the pH is increasing, what we can conclude? We can conclude that upon the addition of the common ion, the pH increases, and that clearly indicates that there is a decline in the H plus concentration, because pH is inversely proportional to H plus, right? And if the H plus concentration is decreasing, that means product is formed in the less amount, right? So this is clearly occurring due to the addition of this common ion. I hope you got this idea. It's very simple to understand with the help of this example. Okay. Now we will do a question. You have to calculate the pH of 1 into 10 to the power minus 8 molar solution of HCl. So this is a tricky question. If you are able to solve it, well and good. If not, don't worry. I will explain it in detail. You have some time to solve it. Your time starts now. You have 15 more seconds to go. Remember, there's a tricky part in it. One hint is for you. If your concentration is having higher acid, that means it must have a pH value less than 7. Okay, your time is up. Now, in this question, what are we given with? We are given with the HCl concentration as 1 into 10 to the power minus 8. Now next, you know that H3O plus concentration is generated from two sources here. In most of the cases, we don't consider these two sources, but here we have to consider it because HCl is present in a very small amount. If you connect it from the HCl, then here the HCl will completely dissociate to give you H plus and Cl minus ion. Therefore, this is the first source. And second is the auto ionization of H2O. So this will also donate some H plus. Now question arises, why are we considering in this case only and not in other cases for water? Because of the much more dilute solution that we are having. If you calculate the pH of this given concentration, you will find it that this value is greater than 8. But the solution is acidic. How it is possible to have a value greater than 8? The reason is that we have not taken into consideration for the water molecule. Okay. So we do it in these cases only where our expectation are opposite of what we are getting. Now we will consider both the cases and calculate the H plus concentration from each of them. First from the H3O plus. If we see, then how are we getting it from water? So due to the reaction of H2O with another molecule of H2, we'll get a H3O plus and OH minus. Further, we know it very well that this OH minus and H3O plus will have a concentration of how much? 10 to the power minus 7, right? So this concentration is 10 to the power minus 7. So we can say that the auto-ionization of water is promoting a concentration of 10 to the power minus 7. But here is a problem for you. There is also a decline in this auto-ionization due to common ion which is coming from HCl. So now what will be the total concentration of H3O plus? It will be from HCl and water. From HCl it is sure that it will donate 10 to the power minus 8. Remember, the common ion effect can only suppress the concentration for weak acids and not for strong one. So it will be 10 to the power minus 8, that is for sure. But let us suppose that this is not 10 to the power minus 7, it is X from the H3O plus. Right? So this is correct. Moving on further, what we can say about the H3O plus concentration in solution? That the ionic product of water always is kept at 10 to the power minus 40. Now, if X is your OH minus concentration, if you're considering this as X, because the concentration of OH minus and H plus coming from water will be same. Therefore, we will consider it as X for OH minus. Whereas the H3O plus will have 10 to the power minus 8 from HCl and X from the H2O. Further, we can say that this Kw will not change its value because it is temperature dependent. So X into 10 to the power minus 8 plus X will be 10 to the power minus 14. Right? If you solve this, you will get a quadratic equation. Further, we know that OH minus, if you calculate this, you will get your X as 9.5 into 10 to the power minus 8. Right? So this is for OH minus. What about the pH? How do we calculate it? So for that, we have to remember that OH minus has a concentration of 9.5 into 10 to the power minus 8. So the pOH of the solution can be given as minus log of OH minus, right? So this value upon the substitution will give you pOH as 7.02. Now the next part is that we know that pH plus pOH is equals to 14. Therefore, if you take this equation and find the value of pH, so 14 minus 7.02 will give you 6.89, 6.98. So this is your final pH. Now this value is clearly less than 7. Therefore, we can accept this value. Now let us summarize all those which we have studied today. If you consider it for a di and polybasic acid, then they can donate multiple H plus. And in that process, your each ionization constant related to each step will have a lesser and lesser value if you move from the starting ionization part. So K1 will be greater than K2. Similarly, if there's a third proton, then it will be less than K2 and so on. Remember, The pH is mostly dependent upon the first step because most of the H plus is directly coming from this first ionization and not from the successive one because of the less dissociation of the further anionic species. Next, we saw what are the factors that affect your acidic strength. First is your HA bond. So weaker bond means stronger acid. And we have seen that the size of the element increases across a group, then the acidity also increases. Whereas in the case of period, as we move from left to right, the acidity also increases because now we have a greater polarity due to extra electronegativity from moving left to right. Third thing was for oxoacids. So greater is the oxidation state of the central metal, or greater is the number of electronegative element in the oxoacids, greater is its acidity. Third was our common ion effect, in which we saw that if you add a common ion to a weak acid or a base, it suppresses its dissociation. Now, this separation is all due to the Leach-Atelier principle. Because of the addition of product, the reaction proceeds in the backward direction to consume that extra added material. We can just see this thing in the case of weak acids. Suppose we considered the example of acetic acid, and we saw that upon addition of the acetate ion, the pH of the given solution increases. That is indicating that the dissociation of the acid is being suppressed to some extent. So this was all for today's lecture. I hope you enjoyed the session. Thank you.